All right, so let's take a look at an example on how we could enforce certain constraints. Right? Let's look at a trivial example like a class that represents an even number. There is nothing in the language that can enforce that particular fact, right? That something has to be even. Right? Instead, we have to use other rules, right? Other algorithms to enforce certain constraints, right? So, for instance, if we declare, for instance, there was no way for us to enforce the fact that the width and the height of our game, we declare them as just integers, right? There's no way for us to enforce the fact that these things cannot be negative. It makes no sense to be negative, right? Even although we went ahead and just declared them as integer, but nowhere, right, where we're enforcing the fact that these things cannot be negative. Somehow we would have been great to have as part of our code, the enforcement of that constraint that these things cannot be negative. Perhaps in a constructor or a builder that threw an exception if the width and the height were negative, and passed in some illegal argument exception, right? Yeah, some things could be ruled out by using just some of the language, right? If the language, you've declared something as an integer, well, the language will guarantee that indeed it is an integer, right? That you won't be able to put floats or strings or characters into integers. So some of these constraints, the language itself takes care of, and we don't have to deal with it. But some things that are logical, such as things have to be positive or even or odd or whatever, or some Fibonacci number, those the language has no support for any of this, right? Instead, we have to use other constructs to impose some of these constraints. So let's consider the simple class that represents even, right? Notice that the constructor here, if you pass in a value, it validates that indeed is an even number, right? If it's not divisible by 2, right? It throws an exception. It says, nope, this is not an even number. I will not accept anything that is not divisible by 2 with no remainders. So the constructor is indeed enforcing this what we'll excuse me, what we'll call in a minute an invariant. Right? The invariance of the value of an even number is that it always has to be even. Right? That's an invariance. And how are we going to enforce this? This is a trivial invariance, yes? But even in your game, right, in your tic-tac-toe or whatever, there have to be certain invariants. And your logic, your constructors, all your methods have to guarantee that certain things always have to be true. Right? Here, the invariance is that the value, right, this int value, has to always be divisible by 2 with no remainder. It has to be even. So we have two ways that are interacting with the value. One is the constructor, which indeed is guaranteeing that this is an even number. And then you have a get value, where you're just retrieving the value. This is a read-only value. So it too is guaranteeing that it's even. It's not modifying it, right? It's just leaving it as noted that it's final. It's the only place where this value was ever added or modified, and we have an exception to guarantee that the invariance is true. Now, how can we guarantee that the invariance, that value, is always even? Well, we have a constructor that throws an exception, and we know that it's a constant after that. It will never change after the constructor sets it, right? So we do have this guarantee that this value is indeed even, right? That never will we get value and return some odd number, and that we'll be able to right? Yeah. So only the constructor ever initializes the value, right? And it's final. It cannot change ever again, right? So we are guaranteed the language using these two rules can guarantee the fact that it's set in stone that this will only ever be even, right? It never changes. So what about if it changes? What if we have functions that perhaps can change the state over time, right? So let's look at just a slightly more interesting version of this, right? What if it's not just an even number, but we have an even counter, right? So an even counter, again, the same thing, right? The constructor can guarantee that the initial state of this counter is valid, right? That the value is indeed divisible by 2. And if it's not, I'm going to throw in a legal argument exception. And I initialize the value. But there's a twist here in that we're now the function here is going to retrieve the next even number, right? So it just counts, 2, 4, 6, 8, and whatnot. Yes. So unlike our previous implementation, right, where it was guaranteed by being final, it could never change. What about this? Right. This is what it's doing. It's just the next value is basically just adding a 2 to whatever the initial state of this class was, right? All right, so looking at this slightly more interesting example, how can we be sure, right? How can we mathematically perhaps prove, right, that this is indeed a constraint that we can guarantee going forward? Well, we have 3 facts. We know that the constructor initializes this and is going to be very, very mad if we don't pass something that is actually even. So that definitely can guarantee that this is an even value. Also, the only way to change this is through this method. There's no other way that this method, that the value of the even counter will ever change. Only through this one public method is the only way, right? And we see that by calling next value, it leaves the state on. It leaves the constraint leaves it the way that is still true. If it was true before, it leaves it true afterwards, right? If it was even before, right, the transformation leaves it also in an even state. So next value preserves the evenness, right? So taking these 3 into account, we can guarantee that the constraint applies, right? Let's look at just some other functions, other methods that would impinge on the value, the even value. So for instance, something simple as reset. So the reset, just resets the counter and puts it back to 0, right? So because 0 is also considered to be even, this method is also guaranteed to leave the state of our counter in a correct state, right? It does not change it into some nonsense state, right? It leaves it also in an even state. So adding reset is okay, right? Adding reset is okay. What about scale, right? So for instance, we want to multiply an even number and factor it, or we want to scale it into something bigger, right? Does this change this? Do we now? But the fact that we can the fact that we can anything that is multiplied by an even number, right, gives you again another even number, right? So knowing this arithmetic fact, we can accept the scale method inside of our counter, right? Because it leaves it again with the same constraint, right? That the number is still even, right? So let's go a little further. How about half? So half takes the original value, whatever value you have, and divides it by 2, and it updates the original even number, right? So divides it by 2. Now this one is it's a little bit that we have to take into account. Wait a minute. Not all numbers, when you divide them by 2, do you get again an even number, right? So you have to be careful, right? So if you divide 20, yes, you get 10. That's good, right? So some even numbers, when you divide them by 2, are still even. But if you divide maybe 10 and you divide it by 2, you get a 5. It's not an even number, right? So this particular method would be, we need to reject this method. This method is not maintaining the constraint that the value is always an even counter. Yes? So we need to reject this, right? Because it breaks the status. We have to reject half and says, nope, no, we're not going to take that. It breaks the invariance. It breaks the invariance. What about half? Half, notice that this one doesn't update the value of half, right? It does not update the value of half. It only divides it and then returns whatever value it is, right? But it leaves the original value untouched, right? So it's okay that we pass it. It's okay that if it's in 20 and you half it, you get 10, and then you get back the 10. But the original value stays at 20, right? And same thing if it's at 10 and you half it again, you get back a 5, but the original value stays at 10. So this one's okay. We can keep it. Right? It does not change the invariance. So all these to say, right? All this very simple, trivial example to say, right? That oftentimes we want to formally, right? Make sure that if something is true, that we are the guarantors of certain things to be true, right? That we have to make sure that all operations, right? All operations. Any transformations that your methods do on a particular data structure, that it maintains the same invariance, right? That it maintains something true and that it does not ever put it in a wrong state, right? That you have to make sure that you identify what your invariances are, right? And make sure that they're always true. And this principle is called class invariance, right? So let's talk about class invariance.